Welcome, everybody. My name is Dennis, and I'm here with Rodrigo. We will present our paper on Lasagne, a static binary translator for weak memory model architectures. This work was done in collaboration with all the researchers whose names you can see on the screen. We present the paper as a conversation between Rodrigo and I. We hope that makes it easy to follow. So, Rodrigo, what have you been doing recently?
Well, I've been thinking about building a binary translator. Previously, Intel's x86 machines dominated the market. Yet, nowadays, we see other architectures, such as ARM, emerge prominently in many domains. This spans many markets, from supercomputers and servers to desktop and laptops, but also in mobile phones. For instance, Amazon and Microsoft now use ARM64 CPUs in their data centers, but also in Microsoft's new laptops, Google Chromes, and of course, Apple's new M1 chips. They are present in their recent MacBooks and Mac Minis. Yet, the problem is that there are many x86 programs in the world. For some of these, it may be difficult or even impossible to recompile to ARM. For example, the source code may not be available. So, I'm building a system that translates x86 binaries to ARM binaries.
Wow, that sounds like a great idea. Have you thought about concurrence programs at all? After all, I imagine that many realistic programs leverage multiple CPU cores. Yet, translating this seems hardly trivial.
Sure, of course I'd like to support concurrent programs as well. Could you elaborate more on this?
Definitely. You say you want to translate x86 programs to ARM. Yet, those architectures have different memory models. That means that memory accesses in x86 and ARM programs produce different behavior. Consider this program. X and Y are shared memory locations, while A and B are variables that are local to the second thread. Now consider the outcome at the end, where A equals 1 and B equals 0. On x86, that cannot happen, while on ARM, this is perfectly valid. After all, CPUs may do out-of-order execution, which means independent instructions are executed in an order that differs from their syntactic order. So, in the example, the second thread reads from X and Y, but because X and Y are different memory locations, these operations are locally independent and may thus reorder on ARM. So, after reordering, the value 0 is read into local variable B, then the first thread runs in its entirety, and finally, the value 1 is read into the variable A. This particular reordering is impossible in x86, so when you translate this x86 program to ARM, it would suddenly allow this behavior, while it would be disallowed in the original x86 program. To avoid the reordering in the ARM program, we could place memory fences. Intuitively, instructions cannot hop over a fence, which means fences restrict instruction reorderings across it. Note also that there are different kinds of fences in architectures. The fences you see on the screen are lightweight fences, which are cheaper than full fences. Yet, they are sufficient to preserve the reordering behavior of the original x86 program in the resulting ARM program.
That seems to be an important issue that must be addressed when translating concurrent programs. As I said, I want to translate x86 programs to ARM, and I'd like to do this statically, which means I convert the entire x86 program to an ARM program, so it can be directly executed on an ARM machine, without an external emulation runtime. The structure of our Lasagne system is as you can see here. In particular, I want this translation to be correct and fast. That is, the semantics of the original x86 program must be preserved, and the resulting ARM program must also be reasonably fast. We build Lasagne using LLVM as its intermediate representation. Once we have lifted the x86 binary to an LLVM code, we can simply compile it to ARM. That allows us to leverage the existing LLVM optimization infrastructure as well as its backends to several other architectures. Our lifting is built on top of Microsoft's Mac tool, which consists of multiple phases. These phases use the multiple representations used by LLVM's compiler, but in the reverse order. It starts with the raw x86 machine code. The binary disassembler simply transforms the raw binary into a very basic representation of its binary encoding. This is still a very low-level representation of the machine code. Then, the CFG reconstruction raises this low-level machine representation into a higher-level representation of the machine code, tailored for each ISA. Here, we have the individual functions represented as a control flow graph. Finally, the LLVM AI is produced in 2 steps. First, we reconstruct the prototype of each function, where we have the return type and the list of arguments. Then, a second pass generates the code for each one of these functions, producing the LLVM IA for the whole binary. We heavily modified this Mac tool in order to support floating point x86 instructions, floating point arguments, and return type, as well as many other x86 features. After lifting the program to LLVM IA, we refine this IA. Through this refinement, we aim to reconstruct some high-level abstractions that were lost during the compilation of the original program. Additionally, we'd like to place memory fences to account for these issues you explained to me earlier about the mismatching memory models.
That sounds like a great idea, but you cannot place these fences arbitrarily. If you place too many fences, performance will suffer. If you place too few fences, your program becomes incorrect. I think it would be a good idea to formalize the memory models. That enables correct and precise insertion of fences. For that, we introduce LIMM as a memory model for LLVM-IR, specifically for lifted programs. Then, we can prove the fence placement is correct, of course, throughout the entire translation process. So we can be sure that the resulting ARM program preserves the memory ordering behavior of the original x86 program. So, Rodrigo, can you tell me more about the IR refinements?
Certainly. Our IR refinement is a peephole optimization, which means it's based on pattern matching. Our goal is to expose pointer operations and avoid converting pointers to raw integers. In this first pattern, we are replacing a trivial pointer cast via integer conversion with a straightforward pointer cast operation. The second example is very similar, but it also computes the offset of the pointer. For this pointer offset, we use the getElementPointer instruction, which is the common way of indexing arrays, for example. By having pointer operations explicit in the code, we can more easily identify operations on the local stack and maybe avoid inserting fences for those operations. Though, how exactly do you envision fence placement works in this setup?
Well, I will simply give you this mapping. This mapping illustrates how memory accesses on x86 corresponds to memory accesses in the IR and in ARM. We know that x86 has a stronger memory model than ARM. So, for instance, to ensure the load instructions do not suddenly reorder with subsequent memory accesses, we place a load fence directly after it in the ARM program. Of course, these mappings are fully proved correct, and you can just plug them into Lasagne. We mechanized these proofs in the Agda Proof Assistant. Additionally, I have proved some transformations for you. While I won't bore you with the details, I will show you an example. This is a read after read elimination. When you have two subsequent memory reads from the same memory location, you can eliminate the second and reuse the previously read value. While this may seem obvious, on some architectures, seemingly obvious transformations are actually incorrect, particularly because it may eliminate dependencies between instructions. Of course, here, I proved this transformation and several others correct on the LIMM model. So you can just plug these in too. By now, we should have a reasonably complete binary translator. Rodrigo, could you check how Lasagne performs in practice?
We evaluated our solution on the Phoenix benchmark suite, which contains multi-threaded C programs. The programs are first compiled to an x86 machine, and then we use Lasagne to lift them to LLVM, optimize the lifted code, and then recompile them to ARM. In this plot, we are showing the effectiveness of our IR refinements. We can see that we're able to significantly reduce the number of times we cast pointers from or into raw integers. In most of these cases, we are simplifying stack pointer operations, as we'll see next. In this other plot, we're showing the effectiveness of our fence optimizations. We can see that the proposed rules have a reasonable impact on the unoptimized code. But combined with the IR refinements, we're able to reduce almost half of the fences because of the local stack operations. These optimizations have a significant impact on runtime, as you can imagine. The fence optimizations alone reduce runtime by 2.6%, and combined with the IR refinements, we more than double that. In the paper, we also compare the translated code with a native ARM binary. Of course, the native ARM binary is still faster, but we're able to reduce the overhead from almost 3 times down to only around 50%. To summarize, current static binary translators cannot properly handle concurrency. In order to address this, we have proposed a new system based on LLVM. We have also proposed several optimizations on lifted pointer operations. We also designed an LLVM memory model that we use to prove a precise mapping scheme. Finally, our solution was mainstreamed into Microsoft's open source project called MacTool. For more details, please look at our paper.
By the way, I'm physically present at PLDI, and I'm happy to discuss any part of the paper. That's all. Thank you for watching our talk.
Right. So you said you. So I based on what I got, like you guys have evaluated this on ARM and x86 conversions. Have you tried any other pairs of architectures?
At the moment, we focused on x86 to ARM, but the paper is on essentially overall like from a stronger to a weaker memory model. Since we are lifting the x86 binary to LLVM, we can essentially recompile to any other architecture. But in this paper, for our evaluation, we only focused on the pair x86 and ARM. But it can easily be extended to other stronger to weaker memory model architectures.
Okay. So there's a question from Hans. So Hans asks, did you consider translating into ARM V8 acquire release instructions instead of fences?
Okay, I will address this. Actually, we could translate it to acquire release accesses. However, there has been earlier results which shows that the performance would be better if we translate it to a simple memory access and a lightweight fence. Hence, we chose this way, but it is always possible to experiment with latest architectures that if there is any change in the performance.
All right, so we have another question from Charita. So Charita says, like, very nice work. Can you comment on how much of the high-level details can be recovered using peephole optimizations? For example, how much of pointer arithmetic instructions can be transformed into get element pointer instructions?
So most of the peephole optimizations we introduce in this paper is to try to reconstruct the pointer arithmetic information, because in the binary everything will be integer operations, so essentially arithmetic over integers. Most of the operations on the stack memory we could recover and reconstruct into like we could reconstruct the integer types into pointer types, and the arithmetic operations over integers into get element pointer operations. So in most cases, for the stack operations, we're able to lift the level of abstraction and reconstruct this kind of information. And this is what allows us to also remove fences around local memory accesses. So yeah, I think that that answers. But in some cases for global memory, that lifting the level of abstraction is a little harder, but so it's mostly effective on stack memory.
Okay.
Thank you for the question.
Thank you. Yeah, thank you very much, Rodrigo and Soham and Dennis, for the talk as well as for answering questions.